All right. So I am Parks Easter with the Exolith lab. Jerry Longfox also helped in making this slideshow. He unfortunately was not able to make it, but sends his apologies and hopes he can make a presentation in the future possibly. But as you guys know, I'm here to talk about Martian simulants. I might go over a little bit of stuff you guys already know, of course, because you are MarsU. So I'm sure you know stuff about Mars, but just to set some up, I'm going to go over some preliminary stuff. So let's just get started here. So what is Exolith Lab? Exolith Lab is a nonprofit under the Center for Lunar and Asteroid Surface Science, survey node, as well as the Florida Space Institute at the University of Central Florida. And what we do is we create high fidelity Regolith simulants. And what that is basically a terrestrial analog for use in ground-based studies here on Earth, as return regolith is too precious. In the case of the moon, we have some of it. In the case of Mars, we have little to none. So, we have some Martian meteorites and stuff like that. But, we have no actual regolith from Mars here on Earth. And we employ a large body of undergraduate students and have a very active outreach and volunteer program. Up until a few months ago, I was an undergraduate myself, studying geotechnical engineering, and now I'm the lead geotechnical engineer at Exolith. So, all right, so just getting some basic info on Mars, stuff you guys probably already know, but it's fourth planet from the terrestrial planet, and it's second smallest in the solar system. Super thin atmosphere of 95% CO2, 2.7% nitrogen, 1.6% argon, and 0.13% oxygen. So, definitely not the same as Earth, definitely a lot different. And it's nicknamed the Red Planet for a reason you will see on the next slide. So why is it called the Red Planet? Mars is red due to an abundance of iron oxide on its surface. Basically, it's covered in rust. Looks just like rust. It has ice caps on the north and south pole, which is really great. As many of you know, water is suspected to have once flowed on Mars, as we can see from many of the geological features. And as you'll see later, these ice caps are really important for water extraction and just other sorts of studies. Mars also has super complex weather patterns, unlike places like our moon, which have no weather. Mars has quite a bit of weather and is seismically active as well. So there is a lot going on this planet. So getting started on the geology of Mars a little bit. There's going to be three main eras in Martian geology history. First is the Noachian, which is 4.7 to 3.1 billion years ago. And it was characterized by a period of very heavy bombardment and volcanic activity. And this is when any of our clay minerals would have formed. In addition, water bodies would have been pretty common. As you can see here on the right, that's an artist's depiction of what it might look like if Mars was covered in water. The next time period is going to be the Hesperian, which is 3.7 to 2.9 billion years ago. And it's going to consist of an extreme geologic slowdown. So it's going to have things like acid rain, sulfuric acid, which is going to cause some of the sulfate deposits that we also might see on Mars. Our current time period is going to be the Amazonian, which is very dry and arid, unlike the Amazon. I don't know why it's called the Amazonian, but it's going to consist of a lot of erosion and oxidation, turning Mars the rusty color that you see today. So talking a little bit about the mineralogy, as you can see on the right, there's a map of Martian mineralogy. I won't get too deep into that because it is pretty complex, and it is an entire planet, so it's hard to dive into one specific area too deeply. But in terms of general mineralogy, we're going to have a few different types of minerals on Mars. We're going to have phyllosilicates, which include our clays, our felsic minerals, which are silicate lacking iron and magnesium. We're going to have a lot of salts, carbonates, sulfates, as well as mafic minerals, which are silicates with the iron and magnesium, as well as iron oxide, like we talked about earlier. So Martian regolith, we're getting into the good stuff here. So regolith is a blanket of unconsolidated, loose, heterogeneous superficial deposits covering solid rock. And While a lot of us would like to call it soil, it's not technically soil because soil has to have a some amount of organics, and no matter how many fossils we find on Mars, I still wouldn't call it soil. But ideally maybe one day we can turn it into soil. That would be great. But for now it's regolith. An easier word to use there would probably be dirt, because as you can see, it does get things very dirty. Regolith is going to be extremely problematic on Mars, as dust storms are really frequent. And I don't know if you guys saw The Martian, but dust storms could easily wipe out a base or do anything like that. So it's definitely something to consider at all times on Mars. And as you can see on the right hand side, that's Opportunity rover covered in regolith. And that's not good. I do know InSight Lander, I think, just announced that it was too covered in regolith, and they're going to be shutting some systems down because of that. So regolith is extremely important when building anything for Mars. It also damages rover wheels. So I believe right now there's a rock actually stuck in the wheel of a rover that traveled I think they said over 10 miles at this point. So, that's really going to damage a wheel over time. No matter how strong your wheel is, rocks will damage it, which is not great. And that's going to be in the Perseverance rover that has the rock in it. So what makes a good simulant? There's a few main factors. So mineralogy is a major one. And that's sort of what we pride ourselves here at Exolith. So many simulants are created using mineralogically inaccurate materials, sort of just to get a maybe geotechnical type of simulant, or just like something that looks correct. But mineralogy affects geochemical fidelity and physical properties. So it's really important to have that correct mineralogy if you're going to make any conclusions based on your simulant or studies like that. You have to, for plant growth studies, you have to grow something in the correct minerals, or you're not going to know if the plant's going to grow. As far as physical properties go, it's definitely important for a simulant to have accurate physical properties as well. Geotechnical simulants do not use the mineral properties, which does not give a natural representation of what we would expect on Mars. So, they might get one factor correct, like shear strength or particle size, but they're very rarely going to get every factor correct because they're missing the atomic accuracy, basically, because minerals have unique properties down to the atomic level, and that really does affect the bulk physical properties of the regolith. So at Exolith, we create mineralogically accurate simulants that mimic the expected chemical and physical properties of planetary regolith, whether that be Martian, lunar, or asteroid. So for our Mars simulants, I'm going to go one by one through the simulants and explain them. But just as a sort of summary, our stimulant is used in a bunch of different ways, primarily to test hardware and processes on Earth before we go to Mars, as it is a very long trip and you don't want to get something wrong here on Earth and then have to figure it out on Mars. So a few of the applications are for any structural applications, plant growth, human health studies are really important, mineral extraction as well, so any ISRU, as well as hardware deterioration. So, any habitat we want to make sure isn't going to get, eroded by the dust storms, as that would not be great. And our simulants are a high fidelity mixture of minerals found on Mars that can be sourced on Earth. And that's one really great thing about, planetary science and planetary geology in general. Aside for a few different factors that can be found in minerals, we're able to source most of the minerals on other planets on Earth, as the solar system formed roughly at the same time. What we do not simulate are some of the dangerous compounds like perchlorates, asbestos, etc. And what a lot of people do is, if they want to test something with perchlorates, they can get our simulant and add perchlorates themselves. It's a lot safer than us adding perchlorates to everything we have, and having children work with that, or any sort of schools or anything like that. Here on the right-hand side, you can see a image from Plant Mars Challenge, which different schools use our Martian simulant to grow plants and test various methods. Okay, so getting into the mineralogy of our simulants, we're going to have all those categories which I said earlier, and I'll go through what minerals we use on Earth to sort of replicate that. So as far as phyllosilicates go, we use smectite, which is a clay found on Earth. For felsic minerals, we use plagioclase, which is just specifically an orthosite, and that's found in Greenland. We source that from Greenland. And plagioclase is one of the most abundant minerals on Earth. It is feldspar, so that's a really great mineral to be sourcing. For salts, we use gypsum. As far as carbonates go, we use iron carbonate. For sulfates, magnesium sulfate. For our mafic minerals, we're using basalt or lava rock, pyroxene, and olivine. And then for iron oxide, which are the fun part of it, we use magnetite, hematite, and ferrohydrite. And I'll get into those in a little bit. You can see here on the right, we have the mixtures, the general mixtures of both our MGS1 and Jezero simulant. And as you can see, some of the very dominant minerals are going to be the plagioclase, basalt, pyroxene, and olivine. And the rest are going to be sort of trace in a sense, even though they are very important. They're going to be a lot less weight percent. So as far as our simulant creation goes, here's an image of the outside area, just right outside our lab. This isn't where we do everything, but this is where we do some of the extra dirty stuff that makes a lot of dust. What we do is we source the appropriate minerals, which have been predetermined by our scientists. Those come in crushed, or we crush them. There's a few that we have to crush, particularly lava rock and bronzite. Every time we get a new mineral source, we use XRD and XRF to verify the minerals and make sure there's nothing that would not exist on Mars in these minerals. These minerals are then measured out using a recipe sheet like you saw in the slide before, and that mixture is going to be put into a cement mixer and mixed for 24 hours. It's going to be mixed for 24 hours to make sure that the ferrohydrite and other iron oxides like oxidize fully after they're crushed or ball milled, and also to assure consistency of mixture. Here's an image of the mixture right before it gets mixed. You can see all the different minerals in there. You know, it looks nothing like Mars yet. And in general, so the way we know about the mineralogy of Mars, it's been gathered by a few different sources, which include rovers and orbiters. For example, our MGS1 simulant, which is our most popular, which is just Mars. That data was gathered by Opportunity, and Opportunity gathered a lot of really important. I misspoke. It was gathered by Curiosity actually, and Curiosity gathered a bunch of different data on the mineralogy of Mars, as well as Mars orbiters that are around Mars today, which helped us with our Jezero simulant. Our goals of our simulant, as stated before, are accurate mineralogy, accurate particle size range, accurate particle shape, as well as that oxidation that I was talking about earlier. You know, Mars had millions of years to, if not billions of years, to oxidize. We don't quite have that time, but 24 hours works well for us. So you saw before the unmixed simulant. It looks a lot more like Mars than the earlier image. So this is our MarsU global simulant. And like I said, it is based on Rocknest regolith analyzed by Curiosity. And it is basically meant to represent the planet as a whole. And that's really hard to do. It's a lot easier to do with the moon and some other bodies. It's definitely hard to represent Mars at, you know, as an entire planet with one simulant, because planets are very complex, and it's definitely going to vary quite a bit from location to location. But this is the sort of average mineral composition that you might see across the planet. our particle size range for all of our simulants pretty much are going to range from 0.04 microns, which is really, really tiny. And we're going to get a lot of that really low size, so 0.04 microns from our clay minerals that we have. A lot of our larger size minerals come from lava rock and other things, lava rock and bronzite, which are a lot harder to break down than those clay minerals. Our mean particle size is going to be 90 microns. And, you know, there's going to be a very wide range on Mars of particle sizes. You know, it's not the case that the regolith is just going to end at 1,000 microns, but 1,000 microns is the size at which, you know, regolith really becomes a problem. And it's going to be, if we ever do use, and we will, the regolith on Mars, it will surely go through some sort of sieving process to make sure that, you know, it's below some micron range. You know, you don't want to be making a clay pot with like a huge rock. So that's just the range we chose for all of our simulants. And as far as bulk density goes, it's 1.29 grams per centimeter cubed, which isn't super important, but it can definitely come into play with some of the geotechnical properties of Martian regolith. And this regolith is used to approximate Martian regolith for pretty much any purpose. You can see here on the right, the mineral composition, like I showed earlier. All right, so getting to some of our more specialized simulants. We also have our MGS-1C, which is our Martian Global Simulant Clay. And what that is a modified MGS-1 simulant that is enhanced with smectite for extra clay. So you can see here that it has 40% smectite by weight, which is a lot of clay. And that's really important for any sort of in situ resource utilization of water. Clays are really good at holding in water, and really, as well as anything that it interacts with, clays are great at that. So the thought is that it might be smart areas that we know are clay rich because they're more likely to hold it over time. And as you can see here, our mean particle size for this simulant is way lower, as clays are anything below 4 microns. So it really brings the mean down, including that much smectite. You can also see that it's a little bit different color. So moving on, we also have our Martian Global Simulant Sulfate. And as I mentioned earlier, a lot of that sulfuric acid rain that happened in Mars's past was deposited as sulfate deposits. So this is also used for in situ resource utilization of water. And what we do here is we enhance the MGS-1 with gypsum to represent more sulfate. Moving on a little bit, we also have our Jezero crater or delta, Jezero delta simulant. And this is going to be based on orbital data of Jezero. And this is primarily used, oh, awesome. It's great. It's great to be able to hold it. And this is going to be used for any studies involving perseverance or really just, you know, anything to do with the Jezero delta or crater. And it's going to be enhanced with a lot of additional smectite, carbonate, olivine. And I'm sure many of you guys know, but, you know, it's a great place because it has such a clay content. And it has all these, you know, it was thought to be an ancient delta on Mars, you know, all but confirmed. But it's a really great place for perseverance to go because it's going to, that clay material and other materials are really going to hold any sort of ancient microorganisms or fossils or really anything that you want to search for in the search for life. Jezero is a great place to find that. So definitely one of my favorite simulants. Now, my absolutely favorite simulant, or at least the one I think is most fun to make, is our Phobos Simulant. And we have two Phobos simulants, PGI-1 and PCA-1. And what these do is simulate the two different theories of how Phobos formed. And these were created for the JAXA MMX Phobos mission, which I believe is in partnership between NASA and the Japanese Space Agency. And we're going to have Phobos Giant Impact and Phobos Captured Asteroid. And these are really interesting because, you know, what we see with the Giant Impact is that it's very representative of the MGS-1 simulant with a few different things added. But the general theory is that something impacted into Mars and ejected Phobos, and then it starts orbiting. Whereas Phobos captured asteroid is a lot different than Martian mineralogy, and it is going to be that theory is that Phobos was simply an asteroid. They got captured in Mars' gravity and is now in its gravity and is one of its moons. And this simulant is specifically used to test, or it was specifically used to test the sample return mechanisms for that mission, which is really cool to be involved in such a amazing project there. And this simulant is also going to be created very differently. So what we do here is we mix all the minerals together, add water, basically turn it into cobbles, and then crush those cobbles up as the sample return needs a lot of those mechanisms. They need to test on larger particles, on like pebbles, cobbles, and test like what their limits are in terms of that. So it's really important for us to have a range outside of 0 to 1,000 microns. So some of the uses of our simulant are in situ resource utilization, which I talked about a little bit, including water extraction and construction processes. Rover testing is very, very essential. Mechanical properties testing, plant growth, and outreach. And you can see here an image of some students growing plants in our regolith. And honestly, that's one of our favorite things to see because it's just so cool. I never thought ever that I'd be able to touch something that resembles Mars so closely, and just seeing everyone interact with the simulant is just amazing. Because it really does, it looks just like Mars, and it's so cool to see in person. So for in situ resource utilization, one of the most popular things, like I said, is water extraction. So testing to see which types of regolith hold the most water, what's the best way to get the water out of the regolith, how we can test or image to see what areas of Mars might have water. And another really cool aspect of in situ resource utilization is construction processing. So I know a lot of people have really worked hard on utilizing the clay in Martian minerals to make bricks, or like you can see on the right with David Carl, he created a cup actually that he was drinking coffee out of, which is really cool. And it's just really cool to see what people are able to make with our simulants. Another really cool aspect of IS3U is going to be utilizing the iron oxides for things like sintering. Because Mars has so much metal, as we can see by its color, that's going to be of huge importance and huge use for any astronauts that are there, or any inhabitants that live there in the future. Utilizing those resources is really important. So that's another really big aspect. For plant growth, which I've already talked about plenty, but it's definitely one of the most common uses of MGS1. Absolutely partially inspired by the Martian, but also it's a huge, something we don't have to worry about as much on the moon or on the ISS is food production. On Mars, it's a 6-month journey away, hopefully less eventually, but food production is really essential. If anything ever happens on Earth, if a shipment ever gets delayed or something bad happens, it's really important that astronauts or inhabitants of Mars are able to produce their own food. And having that simulant and being able to test with that simulant is really amazing and really essential, as it does representation of what it would be like to grow on Mars. A few things that are really important are going to be those perchlorates, like I was saying earlier. That's definitely going to affect plant growth, as well as the gravity. We can't really test growing plants in Mars' gravity, but they do tons of tests on the ISS testing the gravity, and us testing in simulant. We're getting a pretty good idea of how to grow stuff in Martian regolith. Really cool. And with that plant growth, we have the Plant Mars Challenge, which is really awesome. Students participate all over the world with it. And we get to see, various methodologies and levels of success. And honestly, it's one of my favorite things because it's really cool just to see citizen science. I mean, not everyone can get funding, but it's cool to just see like new methods being done by classrooms, because really we need as many plants growing in this stuff as possible. to really get good results there. So Planet Mars actually interacts with, I believe it's sponsored in part by NASA. So, you know, they give their results to NASA, which is really, really awesome. So just a summary, a good simulant is going to replicate mineralogy, both mineralogy and physical properties. And while it might be kind of unintuitive, but I think it's intuitive, physical properties are actually driven by mineralogy, you know, physical properties are not much less than the individual physical properties of those minerals combined into a larger scale. You know, each mineral is going to have a different hardness, have a different chemistry, you know, different size, angularity, and you really can't get those physical properties without that mineralogy. You guys know what Exolith does. We create this simulant, and we do leave out toxic materials. So if anyone ever wants to order it, you know, you don't need to fear for your life for chlorates. We're also able to create any sort of custom simulant if anyone wants any different particle size range, or if anyone also just wants to have a consultation on like a custom regolith or just any regolith order. We do offer free scientific consultations. So, you know, whatever you guys are interested in testing out or growing plants in or anything like that, feel free to, you know, contact us at the email below, exolithlab@ucf.edu, or go to our website and order some there. Just to give some acknowledgements, the work is supported by NASA Cooperative Agreement under Survey, and special thanks to the production team and science teams over at Exolith Lab, because they really pump out regolith. I mean, I think in the last year alone, we did something like 30 tons of regolith, up from 5 tons last year and just in the kilograms the year before. So we love to see the exponential growth and love to see everyone's results. If any of you are doing any science with regolith, definitely feel free to let us know. We would love to see it and share it and everything. Yeah, does anyone have any questions?
Awesome, Parks. Appreciate that. I do have a couple of questions here in the chat section. And I also want to say Cole is in the middle of a dinner and with a dear friend he hadn't seen in years. So he's here, he's around if we need him. But for your detail,
awesome.
This is the MGS-1S that I'm growing. Now I did have to bring it into this little cocoon. It's doing really well. You can see the canopy. That's and amazing. Then I'm finally getting a good response from the primary leads. But just so you know, it works. Also, I'm a buyer of your Jezero, and I'm also a buyer of your MGS-1S. I'm also using the MGS-1S and infusing it into a cyanobacteria that I'm using, that I'm hoping to have on Mars at one day.
That's awesome. Yeah, that's
amazing.
Help.
Yeah, and for your information, Dr. Kevin Cannon, Dr. Daniel Britt is how I found you guys, and to this day, I'm thankful for that introduction. But one of the questions I thought was really interesting here, and it said, sorry, I might have missed it, but for the plant growth simulant, where does the nitrogen come from?
Yeah, so that's the big issue. And you know, as you saw, if you watched The Martian or just to know anything about like Mars in general, that's what we really have to add. And you know, one of the growing, well, there's a lot of ways to do it. I mean, one idea is, you know, recycle any waste that is produced by those initial astronauts, add those to the soil. Or regolith, it'll be soil at that point after we add that. But and another, you know, like you were saying, bacteria, adding bacteria is a really good way, or just any kind of modification or like bioengineering of the regolith is how you get that nitrogen. I mean, are you growing that plant in just regolith, or did have any additives? Or
great question. I'm actually using 87.5% MGS-1S, and I'm using 12.5% of a bonsai soil.
Okay.
And I'm also surrounded so the cocoon itself is the potato plastic, I like to call it that. But I'm using a sphagnum moss as a kind of a source of constant fluid, so that I don't have, if I'm on, if I'm off world and maybe I'm on ISS, I don't have water flying around. I'm actually in for the next several days, and I've been here for almost 2 weeks. I'm in an analog mission here at the University of North Dakota, and I will publish all of this eventually, and enough about me. Let's continue on. Andrea had a question about seeing if we could get links to the Exolab Simulant. So I'm just typing that in here right now, .com.
Yeah.
And there, I just did that for her. Ian, given the number of hydrous minerals in your MGS1, will it be substantially affected if you put it through the desiccator? Great question.
What is the desiccator? Okay.
Like something like an oven, like a little bit of like a mild oven, like they use in chemistry.
It actually would kill it, I think, wouldn't it? Or if you had, those minerals, it might, some of them.
Yeah, and one sort of issue, we produce all this in Florida, so it's very, very humid. So there definitely is like a slight water content in those minerals. But that being said, Mars atmosphere isn't perfect. So there's definitely, I would definitely put it through an oven, especially the clay minerals, put it through an oven before, use. But, if you're anywhere humid like we are, as soon as you take it out of the oven, it's going to rehydrate basically. But yeah, you would think there are a lot of really hydrous minerals in there. I know when we get them, we try to make sure they're as dry as possible. But I'm sure it would definitely change some stuff if you tried it out as well.
All right, I'll take that into account. Thank you.
Great question, Ian. He's got another question here too. Go ahead. Sorry, Parks.
Oh, I was just gonna say, in response to the nitrogen question, Mars atmosphere does have some nitrogen as well. So, if we're able to somehow extract that from the atmosphere, it would be, we could possibly use that. And I know we're getting better and better at extracting stuff from the atmosphere. So I think, there was some, I forgot the name of it, but there's some mechanism right now on the rover there that I think extracted some of the elements from the atmosphere as well, right? For breathable oxygen.
That's correct.
So that's really awesome.
That's the MIT labs came up with. It's called MOXIE. MOXIE is brilliant at pulling oxygen and other various chemicals out of that atmosphere, and it's using a real low temperature. It's not actually obnoxious as the temperature goes. I've got another question here from the MarsU folks. It's curious on the regolith properties such as dielectric, electromagnetic, 3 to the 8 Gs, etc. I'm personally interested in the electromagnetic side of things, and that's one of the big parts of my research here at UND and then back in San Francisco. So, and anything about that dielectric, electromagnetic?
Well, it's definitely magnetic with all those iron oxides and everything we add in. And it gets over everything. It stains anything you put it on. We haven't done I know we have done some magnetic susceptibility. We haven't done a huge amount of other like magnetic and electric testing on it. So I don't have any specific answers for that. But I mean, yeah, we honestly rely on great researchers like you all for a lot of that research.
That's a great question, MarsU, because we actually plan on throwing that in our electromagnetic generator that we created, the pulse generator. We want to see what it does, if it pulses and if it moves. That's exactly what we're going to do. And Ian, speaking to that as well. And the next question, Ian, I'm going to save you for one of the last. It says AC to everyone, without adding the nitrogen, will legumes that fix nitrogen grow without supplementing it? That's a good question. I have not had very good success with that. I've had to add a little something to it.
We found some really interesting results. And this wasn't actually specifically with our MGS1. We actually, relating lunar a bit, both simulants, if they don't have the nutrients, they shouldn't grow. We found that actually a lot of them do sprout just because of their internal energy and nutrients, that they're kind of born with, or that they have stored inside them from their
that's a good point. The exudate has a little nutrition to it, so when the seed pops and that that gel that comes out of the seed as it hydrates, that has a pretty good source of nutrition for the seedling. And that is a very good question too, by the way, because I have noticed that I am getting good growth initially. So that's why I thought if I added just a little of the some type of some biologic, some kind, I get good luck, and I have.
Yeah, and there's some really interesting ways to get around this. Like you were talking about Moxie, it possibly could get some nitrogen out. Also, I was just talking to someone today about the fact that if you were able to successfully sustain like an insect colony or something in the soil, like maybe an ant farm, as the life cycle goes and those ants die and sort of like fertilize the soil with their organics, it is possible because insects are very low maintenance, probably one of the most low maintenance things out there. Even if we try to get rid of them, they don't go away. So that's a really really interesting way that I've thought. If you could successfully maintain a colony that sort of fertilizes the soil itself, you could successfully do that and then start a plant growth sort of colony, which would be really cool.
Definitely. Hey, Parks, do me a favor so that we can pull up some of the participants here. Can you end your screen share? And then let's go. Hello, everybody. We've got a pretty good turnout here. It's nice. I have to say, I'm very impressed with the quality of the simulant. I know Dr. Cannon was a really big believer in the 1S, and so you elaborated on it, but the perchlorate is a real issue, right? The salts themselves. As I'm watering, right, as I'm running water through that simulant, are you finding that perchlorate or that heavy salt, or does that accumulate at the bottom of my little pod? And is it real salty down here, not up here, that kind of thing?
It very much does. And I haven't seen it exactly in the plant growth studies, but specifically in making the PGI, because we turn it into cobbles and kind of like let it dry out for a while. We see a lot that once it turns into the cobbles, the salt basically goes towards the outside and just forms like crystals on the outside of it. And you can really see the salt on the outside of those cobbles when you're like crushing them or doing anything with them. So I would definitely say the salt is a major issue. And I've also where I don't know how valid this is, but supposedly the perchlorates are pretty easy to remove from the regolith. It's not really an issue of removing them. It's just when they're there, they're really harmful. But I know there are some ways, and I don't know the exact methods, but I know there are quite a few ways to remove that perchlorate from the regolith, which is, we're kind of at the assumption, we're making our simulant with the assumption that, it's already been removed, so go grow your plants rather than rather than have it all in there.
We're hoping that at the molecular level, we get some type of a bind to that heavy salt, and then that pulls it down and I'm using some various things, by the way, for that. I have another question here, AC, to everyone. With all the hematite that the regolith should center with microwave energy real well for preparing solid surface for building and launch pads, that's a good question. Could we use your simulant to make concrete? I don't know if you call it concrete, MarsCrete.
Yeah, no, that's a huge application in ISRU. The sintering with all those metals, and I don't know necessarily if you would sinter the raw regolith. I suppose you could. It would just be imperfect in a way. But absolutely extracting those minerals from the regolith, whether it be through molten regolith electrolysis or some other methodology. It might be easier, since it's a metal, to just use like something magnetic. I mean, actually that'd probably be the easiest way, is to use a magnet.
Copy that. Our founder, one of our co-founders, has a question. Mr. McKenzie, take the field. You'll have to remove your microphone, or turn your microphone on, Bruce. Here he comes. Bruce. Okay, moving on real quick. Bruce, when you get back in, just turn your microphone back on. Ferry Borse has a great question. Elon Musk said life on Mars won't be luxurious, and that's true. It will be cramped, difficult, hard work. He said in an interview that living on Mars will be dangerous, especially at first. Insider previously reported that a human without special equipment would die within minutes on Mars. Any comments on that? Well, I can attest to that. Life would be brief on Mars without a habitat, and I can tell you that for a fact. You will die pretty quick. Anyway,
And you're in the habitat right now, right? So is it cramped and crowded? And
well, you know, it's the UND has it was a NASA supported habitat, so it's huge.
Okay.
I've got a really big geology module. The plant module is massive. I've got multiple racks. We're actually using some of their original KSC lights that they had. It was by BIOS. They're
that's awesome.
They're brilliant, but they're very hot. I can tell you right now, and it's a really hot environment. Let's get Bruce. Are you? It says, "Oh, that's my fault." Oh, there we are. Well, I can do that. Has to, and then I will just ask to unmute. There you go, sir. I think that might do it. I don't know. I'm not a professional expert on this in this environment as it relates to Zoom. And I do have another question from AC comment. Bruce, were you able to get on there?
It might be in security if you have that setting. I'm not sure.
It might be, yeah. You know, it's brilliant that we have a great team here, but I'm not seeing that. I see chat, share screen, advanced sharing options. Yeah, you're not. I'm definitely more of a space studies scientist than I am a Zoom operator. Bruce, do you just want to chat it in there, or? Yeah, is anybody able to see Andrea? She could speak right now. I think you guys are all unmuted. You just got to unmute yourselves. Could be wrong. AC to everyone. Perchlorate can be persistent in the environment, and studies have proven microorganisms can reduce perchlorate. An electron acceptor to innocuous chloride and oxygen under anaerobic conditions. Brilliant. Well said. Thank you, AC. AC is what I wish I had in here right now. That would be air conditioning. But the plants are enjoying it. Yeah, that's there. Maybe. Oh, there you are. Hey, good to see you, my friend. Always awesome. I don't know if I can unmute you, but there, I'm trying like heck. Apparently not.
It's okay. I mean, like you're on the Mars base, so we have the delay anyways, a few minute delay.
You know, it's funny. I had to, for the past 2.5 days, I had to simulate that. On open participant list next to Bruce, click make host. Oh, aha. I am doing that now. Participant list. I'm clicking on you, Bruce. I'm going to make you host. Watch out, here comes the pro. Done. Take it away, Bruce. And Parks, are you in, are you at UCF?
Yes, I just graduated with my bachelor's in geotech, but I've been working at Exolith for over 2 years, so.
Awesome. Yeah, I think you might have been in some of those spring seminar series that Dr. Britt had in 2020.
Yes, I think I was.
Yeah, and I was in there with you and Dr. Aboud Madrid out of Colorado School of Mines. And yeah, it's a brilliant place. Bruce, are you able to get anything on there? I've made you the host. You are You're the hostess with the mostess. Nope. Okay. He probably gave up on me. Don't give up on me. Promise I'm here. I love AC. I love your backdrop. That's beautiful. Those, the horns on those. And Parks, I could be wrong, but aren't you right next to or very close? You're 30 miles or 50 miles from KSC. Is that right?
Yeah, we're extremely close over there. Very close. We work very closely in partnership with Swampparks as well. You know, if you guys know anything with them, I'm working with them all the time. It's great.
Who's the main person there? I remember there was one of the lads that was in. What's his name?
So Rob Mueller is who we work very closely with. We also work closely with Phil Metzger, who is the other co-founder. So
that's right. Phil and I are we are in chats occasionally. Look there for.
Oh.
Okay, and now I'm unmuted again. Awesome.
Yeah.
I have to say, I haven't dug into the Jezero crater simulant yet. Have you heard anything about its, is it receptive to seedlings and growth, et cetera?
You know, considering, you know, if it was one of the locations most likely to harbor life on Mars, I would think plants would do particularly well there. Especially, I know it has a lot of different minerals in it. So I think it would have a lot of the minerals that would be required, you know, for plants.
Well, I'm going to give it a go.
Yeah, no, I hope it goes great.
Yeah, I have been reporting in occasionally. I get emails from one of your team members asking for my results, and I've been.
Yeah, we love to see it.
Yeah.
Awesome.
Yeah, it's pretty cool. Hat Creek, that's probably one of the most famous radio observatories on the planet. Does anybody else have any questions? Bruce, did you ever get unmuted? Were you able to hop in? I know we all love hearing from you. Oh, Parks, you're the host now. There you go. You're in charge.
Yeah. I was just yeah, I think it might be on Bruce's side. I don't know.
Yeah, I think so too. Yeah, because I know AC, he was able to unmute there, and so was Andrea. Or Andrea, I know you and I have been friends on LinkedIn for a while. A premier educator, guys. She represents us well.
Awesome. Yeah, I would love to participate in some other MarsU stuff in the future. I mean, I was looking at the stuff you guys do. It's really awesome. So
we've got a couple of, we're already planning out to a couple of years. I know Bruce and Cole have really done that, and I'm just a fly on the wall. I'm sitting there just listening to their brilliance every day, or every other day. And Cole has done wonders for a lot of my research. And we're using your Regolith practically every day.
Awesome. Yeah, let us know if we can do anything to, if you guys need any custom simulants or anything, we can always do that. So
you know what I like is I like your sign, the Exolith logo. It's really pretty.
I had no part in creating that, but just the name and sign alone is great. I mean, it's the perfect name, perfect sign.
Definitely. We've got a great crew. Ian, was there anything else you wanted to mention? I know he's muted now, but I know he had anything at all.
About why I asked about hydrated minerals. I was just going to be doing bioremediation on the simulants and using microbes in solution. And I was just wondering if I could, in theory, filter out the solution later without affecting the hydrated minerals. But I don't know if I can, given what I've heard.
Yeah, I'm thinking if it does have any clay in it, it's going to have some trouble. But like I said, I mean, if you ever sort of make sure that it's just the iron oxides and everything excluding the clay, or the high, to totally do that if you just ask us or send us an email. Because I mean, it's going to affect it somewhat, but If you do need to reuse it a bunch of times, you're probably better off just leaving it out. Because you could always filter that out on Mars before you do anything as well. So,
That's true.
you know,
That's true.
yeah, as long as you're using the minerals that are there, you're good.
I can't, and Ian, I just so you know, and I know we're supposed to meet up either this summer or in the fall. I'm actually using dried spirulina, which is blue algae cyanobacteria. I'm using that as a feedstock now during my simulant testing. So this particular plant has been fed for now 3 or 4 days, three days now, twice a day with about an ounce total of spirulina and water. And,
So like a fertilizer?
Honestly, I'm using it like a fertilizer, and this is the most I've gotten in terms of growth to get to this this little piece that's coming out right there. So I'm very, very excited. It's part of a closed loop system that we're also developing. So, which I think you know about, and we're working on.
BLSSs.
Yep.
All right. Well,
you called it. We'll
Yeah,
see how it goes.
Good. I guess I could. Well, I might use it as another control of my experiment, but
it's a brilliant control rather than just water and something else. That's a great idea.
All right,
Andrea,
I'll think
see you
about
around.
that. We'll see you then, and I'll plan that out sometime this week or next. Thank you.
Yeah, I'm around. Any questions, reach me anytime.
Terry, I'd like to make a comment, and as
anything, yes, sir.
Curiosity, and that is what you read, what I wrote in the comment about Elon Musk saying that how cramped it was up in the Mars.
Yeah.
I want to make a comment and find out about your opinion. One of the reasons that it is going to be cramped is because the system of the building that they are going to be used in Mars. There are a number of simulations that prototype houses or igloos that have been made, and it is being made with an invention of Buckminster Fuller about 100 years ago. So that system, in my humble opinion, with respect with all of you, I truly believe that system is not, that is one of the reasons because it is going to be cramped, because that system was not made to be for fast construction. So for that reason, at the University of Western Sydney, I have created a modular system of building that is very fast and it is very easy to assemble. For example, if you want to have a lab or you want to have a nursery or whatever you want, you will have to take only three pieces of how would say components with you, which is quite lightweighted, and make a voluminous, quite large. It will not be cramped, and it is very easy to carry every pieces up there, and astronauts can only join one bolt and join them together and even build a high-rise building that is seismic proof. That means if there are earthquakes on Mars or the moon, it will take huge dynamic impact on this system. This is what I want to know, and I have made a 3-4 minutes video of my simulation, how we are going to build with my patented, in US patented system of a modular system, that how we can join and build something which is not cramped, and it is actually all the astronauts can stand up their feet rather than to go like a fish in an aquarium. This is only my comment from my previous observation.
It's a brilliant comment, and I'm going to turn it over to Bruce too, because I think that's a brilliant idea. Bruce, take it away.
Terry, can you hear me?
We hear you perfectly fine.
So Parks, you're the host now. Would you please try to unmute everybody? Because only a few people have been able to speak.
Yeah.
And if you don't know how, then send it back to me. So I logged in on a different device when I came in. Okay, we hear Lily. Good.
I just got it. Just must have stopped.
Awesome. Okay, good. Yeah, so I think if I had to log in a second time in order to speak. Don't know why. So Parks, way back in 1988, I came up with some masonry construction. I think I was the first person to propose practical masonry construction, sealed with regolith on top for pressure, and that got written up by Stan Robinson in Red Mars. So I'm very interested in sintering your simulant. Can you tell me how that coffee mug was made? Was that sintered? Was it baked? Was it molded? Was it glued?
That's a great question. I do not think it was sintered. It definitely looked sintered. I do know the person that made it though is very into making ceramic.
Sure. Yeah. I've also
information if you want to reach out.
Yeah, I've also proposed making simple ceramics on Mars. As far as Fairbore's comment, I think once we start making things from local materials, it's just a matter of time before we can make things more and more spacious and get more interior space per person. But as long as you're bringing either fixed or inflatable habitats from Earth, it's going to be cramped just to save money. Let's see, for Parks, I have been told that there is no asbestos per se on Mars, but there's a mineral extremely similar to asbestos that has a long fiber. And for the rest of you, the reason asbestos is dangerous in your lungs is the white blood cells recognize it as a foreign substance and they try to engulf it, but the asbestos fibers are so long they stick out both ends of the white blood cells. And so as the white blood cells extrude whatever it is that decomposes foreign particles, it leaks and damages the lung. So Parks, have you heard anything like this? Do you know the name of these minerals? That whether it's asbestos or something similar?
So I have heard that there is a certain amount of serpentine, especially from some of the early results found in Jezero. There is some amount of serpentine on Mars, and serpentine does have a mineral or I guess a form called chrysolite, or I think it's how it's pronounced, chrysolite. Or chrysotile, and that is an asbestiform mineral. If there is another like long, strict sort of fibrous mineral that only exists on Mars, we definitely wouldn't be able to simulate it because
Right.
it only exists on Mars.
No, this was some mineral that also exists on Earth, but we've only studied asbestos in detail about the health effects because it's so commonly mined and had so many people got asbestosis. And this other mineral was not studied and was not thought to be harmful, but they didn't know. Okay, another question. You try to make your simulant similar mechanically and chemically and color. And it's great because I was at a teachers conference years ago and they were selling there were some companies selling lunar regolith that had the chemical composition was completely different from the moon. They were only worried about mechanical similarities. And they were selling this simulant to high schools to grow crops in. And it was just had no chemical thing at all. Anyway, my question is, if we want to do some studies that are only looking at growth or only looking at texture or only looking at color, could you mix up a batch and sell it cheaper? So for example, if we only wanted color, or maybe we only wanted large grain size so that kids can play in a Mars yard safely without inhaling it, could you sell us a ton of play Mars dirt that is simpler for you to make?
Yeah, no, absolutely. And we do that a lot with our lunar simulants. We haven't particularly had many requests for a huge bulk Mars order yet.
Yeah.
Probably mostly as a funding issue.
Sure.
But just in general, yeah, totally. I mean, there are simulants out there, and I know, one of our main ingredients in our simulant is lava rock. And, you could get a red lava rock and combine it with an orthosite and a few of the other minerals that aren't harmful. Maybe leave out the iron oxides so it's safe. for kids to play in, and that could be sold, at bulk
Sure.
much more easily than having the 24-hour mixing process to get everything to oxidize. There could definitely be a
Okay. Yeah, good. Yeah, we might talk to you about that. However, what you're competing with, I was out west somewhere, and I just scooped up a bottle full of red sand from it might have been Boulder, Colorado, might have been Arizona, and I've been having that as an exhibit when I exhibit to school kids, as this is the color of Mars. Anyway. Let's see. Is there anything that we can do to help your company? Publicity, or should we make up, instructions for how to do a certain experiment or how to manufacture something from your simulant, and we'll jointly publicize,
Yeah, I mean, I'm currently working a lot on developing curriculum for Exolith. So selling plant growth kits and stuff like that. And we would love to reach out once we develop that kit, and maybe collaborate on publicity. Sell plant kits, have people grow them.
Okay. But my question is, what can Mars University do to help your company? Preferably that doesn't cost any money for us, or that we'd be doing anyway.
Yeah, I mean, just getting word out, sharing any sort of scientific publications, or like Terry was doing, just responding. Sharing posts and just giving us stuff, giving us feedback on our simulant, and giving us cool stuff to post that you guys work on. That'd be the best.
Okay. If anybody else wants to talk or be visible, try to unmute. And if you can't, then type in the chat that you're not able to.
Hey, I'd like Andrea to say something about her victory and what it was that she used. How? I mean, what a brilliant success story.
Hi.
Hi. It's awesome.
Hi, everybody. Can you hear me okay?
Yes.
Great. Okay, yeah, this is totally in my wheelhouse. So I started off as a ceramic major, and I actually went to college on a ceramic grant, and that's how I got into school. So I'm a ceramic artist, and then that parlayed into physics, and now I teach astrophysics, and I do a lot of work for NASA in the education department. And the last 10 years I've spent a lot of my time working with simulants, Regolith simulants, lunar and Martian, and blending that and making clay bodies out of it, working on the wheel with the simulants, and just doing materials testing with my kids. So I've got 34 years in the classroom, and I'm a specialist. So I travel around and I teach primarily physics, but I'm also a ceramic artist. So I took the two fields that I love so much and I combined them. So what you're talking about is completely in my lane. So I entered a contest with the material science, it's ASM, and they're a national organization. And I created a curriculum based on making space bricks and using different formulas from lunar regolith and Martian regolith. And I created a whole program, educational program on it, and I won. I submitted it and I won the contest. I just found out about 3 days ago.
That's awesome. Congratulations.
It was a national contest. And so we did aggregate, composites, all the different breakdowns of the different material science exploration that you do with kids. And we did the formulas, the different recipes, formulations, whatever you want to call it. And then we also worked on structure building. So there's a combination of the engineering and structure and also material science. And we did tensile strength, we did impact, we made, I call them pucks, like little hockey pucks. And we had forms and we made them, we used different compounds in different formulations and dropped them from a 3-story building to see which was the strongest. And then we did tensile strength testing, and then we did structure building. The whole program.
That's really
That's
cool. I mean,
that's brilliant.
if any of this is public, or you would
No,
ever like to reach out or anything, that'd be amazing.
Yeah, here's my weird deal here, because it's even weirder now because the COVID thing, all my schools got shut down. My students are kindergarten through 5th grade. So, I mean, who doesn't, I mean, let me ask you, do you know any 4 or 5-year-old that doesn't like to make mud pies and do it in class, get a grade on it? So I created the whole program myself. So I have a background in material science, as I mentioned, astrogeology, and then I do a lot of work with NASA. But I took my background my core background as a ceramic artist. So I took all that knowledge and just combined it, and I do all my own research and testing, and I write my own curriculum, and nobody really knows I'm doing it. I'm just kind of doing, I'm a silo. I'm just like operating on my own, and I get contracts with school districts, homeschool organizations, charter schools, and I contract with them directly, and I'm a hired gun, and I just go and do my programs. So nobody really knows what I'm doing except for the kids.
That's awesome. That sounds amazing.
So I don't know. I mean, it seems like there's a love connection there, right?
Feels
So,
Yeah.
I don't know where we go from here, but I did get your information about the Regolith and the simulants, and I asked in the chat for the links. And I mean, I don't know where we go from here. We could probably help each other.
Yeah, that would be amazing. We'd love to collaborate in any way. So.
And I'm currently working right now with Texas Mining Resources Agency, and also the Nevada Mining and Minerals Resource Agency. So I'm working with those 2 organizations, and we're thinking about, I'm looking for money. I have somebody that has $1 million grant, but I'm looking for my own money to start a Martian yard, so that I can do testing, robotic coding on the Martian yard, just like JPL does. And also a simulated Martian garden. That's my wish list.
Hi, Andrea. One thing that comes to mind is Kai Stats at Biosphere 2 is creating a Mars yard. He's got kind of the cement floor and the walls, and the roof is going to go on soon. His program is called SAM, S-A-M, but it uses some of the Biosphere 2 facilities, and you can write to Cole or myself or Terry and get that contact.
So how do I get your guys' contact information? I mean, I'm just going back and forth on chat, and I'm copying and pasting.
Yeah.
Andre, you and I are friends on LinkedIn. You and I've talked several times.
Yeah, I know. I recognize your name. I go, wait, I know that guy.
Okay, so Andrea, I just put my personal email in this chat, and I also put the general Mars University email contact, which is info@mars.university. Repeat, info@mars.university.
Info@mars.
Correct. University. There's no .org, there's no .edu, there's no up and down in space. No .com here, just mars.university.
Well said.
And you can put your email in the chat if you want to, or you can send it.
Yeah, I'll put my email in there, and then you guys can find me on LinkedIn too.
Yeah,
because
okay.
I'm not very active on LinkedIn,
Sure.
but I'm connected with all the right people, that I need to be connected with. It's more of a push instead of a pull. I'm kind of passively on LinkedIn. You know what I'm saying?
Right. Me too.
So
And
I
part-
just wait for someone to find me and then I follow up on it. I'm just.
And Parks repeated his address in the chat. Parks, you have a University of Central Florida. I thought this was a corporation you were running. Is it more of a university project?
So it's a little bit of it's definitely not a corporation, but it is a slightly separate entity from UCF directly. We're part of UCF in addition to part of the Center for Lunar and Asteroid Surface, in addition to the Florida Space Institute. So we're very, very closely associated with UCF. Our lab is at UCF. We just have a bunch of different aspects, really.
AC asks, how well do the simulants fire in kilns into ceramics? Does anyone know if they are electrically conductive afterwards? I will say a lot of ceramics are not electrically conductive, but I'm sure it varies. Do anybody know about firing in kilns?
Andrea does.
Well, yeah, that's what I do.
So okay, that's a question from AC. So AC, do you want to ask? Do you want to refine your question?
How would we test it for electromagnetism?
No, electroconductivity. So one thing I've wondered about is if I want to transmit a lot of electrical power, let's say I have, a big solar farm to the east and a big solar farm to the west, and I want to hook them together and make a bunch of wires. Can I just lay them on the ground? Could I manufacture a glass insulator and put it on top of a rock? A lot of times if you just take dirt from Earth and get it hot enough, it gets sort of glassy, and most glasses are insulators, but I don't know about Mars. So if anybody has an insight in that, let me know.
Well, I mean, I'm not a scientist and I'm not a chemist. I just play one on television. No, I'm kidding. But my experience is that I have a lot of ceramic ware, obviously doing this since I was a teenager, and none of it is conductive.
Yeah. Hey, well,
it just isn't.
Have you actually tested with a voltmeter?
No, I haven't, and that's a good thing to do. I haven't had the curiosity to actually do that. I just know that a lot of my clay bodies that I happen to work with are very high in iron because I like the red clay bodies, and I just happen to gravitate towards it, and which are high in iron. But once you fire them, you have the vitrification of the high temperatures. So you're basically melting all the silicates in the clay body, and for some reason, there's a chemical explanation for this, but for some reason they're not magnetic any longer.
Yeah, well, there's a question of magnetism and also a question of electroconductivity.
Yes.
So let me say what I know for the rest of the people. Most thermal conductivity is done by free electrons. So in a metal, you have a crystal structure of metal ions, like iron ions, and then you kind of have a cloud of electrons that can float freely through this crystal structure. So and if a material is electrically conductive with these free electrons, it's also thermally conductive. There are a few materials that can conduct heat, but not electricity, but very few.
That's interesting.
AC, are you able to unmute? No. Okay. Parks, would you try again to unmute everybody or transfer host back to Cole? And actually, Cole isn't here, so don't do that.
Yeah, Cole's here now.
I don't see him.
Yeah, he just gave the peace sign. He is the host. There you go, Cole.
Hey. Oh, I see Cole. Yeah. So Cole, see if you can unmute everybody. because I was unable to on my smartphone, but I might be able to on my laptop.
I'm asking AC to unmute now currently, but I just asked everyone to unmute too, but we
Okay,
still
thank
can't
you.
hear AC.
Parks says you're getting into Tesla's technology. Ha ha ha. I think Parks, you can say that yourself if you want. Okay. Let's see. Any other questions?
Hey, yeah, I wanted to jump in and Parks, that was a fabulous presentation and really interesting, and love to see what you're doing, and think we look forward to building the bridge.
Yeah, thank you so much for having me. It was awesome. I would love to collaborate in the future.
Okay, so Parks, I'll contact you offline about sintering, and Andrea, I can show you some designs for Mars habitats made with bricks and other things that you might be able to make a model of, and do that with your kids.
Wow, how fabulous. Thanks. That'd be great.
Here's kind of some near-term potential collaboration as well. We're going to be exploring a lot of these Mars analog environments in early June or early July, most likely. And so, we'd be glad to help collaborate and specifically quantify and characterize the local mineralogy here at these Mars analog sites and compare it to Simulant's potential.
Yeah, that would be awesome. I mean, if you guys end up like getting samples or anything, we could totally compare it to our MGS-1 with all the tests that we do. That'd be really cool.
Okay. Well, we'll be collecting samples, yes, with our students.
So hold on, I didn't know if I was unmuted. So your analogs, that's on the slide you're showing?
Yes.
Well, these are just a bunch of locations that look similar to Mars, or they have a climate, very dry, or they'd be good for testing. But different locations are good for different things. Like MDRS has a lot of bentonite clay, and there were people who made bricks out of this bentonite clay at MDRS, and they just crumbled. It was nothing like what the Mars regolith would really be like, but it looks like Mars, and it's a really good place to practice Mars missions. Just don't make bricks out of bentonite clay.
And what if, like, we come across a gem, and there's like major tons of very similar dirt that's comparable to Mars, that might be used for experiments testing.
Well, then we'll sell it, and we'll put Parks out of business, or Parks will use you as the distributor. We will be your wholesale source.
If you guys find a site, let us know.
Yep.
We can definitely collect samples, and we'd love to discuss the XRD and XRF analysis too.
By the way, on the top row, the third one over is Little Painted Desert north of Winslow. I think that's Arizona. That is very similar to MDRS, where Mars Society has their station. And what it is, it's alternating layers of sandstone and clay. I think they've got a white, a red, and a gray, alternating layers. Anyway, and so the different layers are completely different minerals.